channel.
Yes, thanks. It is going to be on a little different layer, much more low level. The reason is that we most of the time we implement programming languages, most of the domain-specific languages, and try to bring benefits of declarative programming to less fortunate environments. And between us, we happen to have also a couple of years of practical professional experience in fields of scientific modeling, simulation, real-time programming, and also music. Marcus is also a trained musician and composer. And born out of our frustration will be established tools in all of these three areas, and because of the similarities that we perceive, we started to develop a programming language, and this is called SIG, which should work equally well in all of these three. I'm going to show you the music incarnation of SIG, if you like. So, obviously there's a lot of people doing exactly that, creating languages for these kinds of problems, so why bother another time? Well, there is a large range of visual data flow programming tools. Think of Simulink in the engineering field, or Max in the music business. And they have some very good points. They're usable by domain experts. You can create very complex networks of computational components. And we would like to have that too, but with semantics. So we want to have types and static type safety, and also a system that's really declarative and that has a formal specification that says what it does, and it does that all the time. And then there is the French school of synchronous programming languages like Lustre or Esterel, and they have some very good points too. In particular, they have very rigorous, very simple semantics, and that's because they are very specific about how time is modeled in these systems, and it's very carefully designed with respect to the model of time. So we would like to have a little of that too, but we don't want to be quite so low level, so we want to have some decent support for high-level programming, for abstractions, for reuse, and also for very important for symbolic computation. Let's say with right data types. And finally, of course, there's functional reactive programming. The relation of our functional reactive programming is very interesting. I would be happy to discuss with any of the RFP guys afterwards. Simply put, we would like to take the same idea of writing down computations on the value level and lifting them to some time-dependent model, and have all the nice things of purely functional programming. But we deal with discrete time only. So we're far less ambitious with respect to how time is abstracted. At discrete time we have a clock, so signals are really streams, and signal processors are stream processors which can be described as automata. And then the semantics is found in ordinary math. So types are sets of values, functions are functions. None of the fancy stuff that says theoretical computer science apart from the rest of the educated world. Right. We have thought about these things for a very long time, and finally we have come forward with a semantics paper at MSFP earlier this year. And you're going to see the first serious demo of the implementation. It's written in Java, uses the things that Java has for interactive input and output. The whole compiler is written in Java, so I'm going to type something in. It's transformed a lot behind the scenes, and then there's a Java-based interpreter. And if things need to go really fast, there's also a compiler that compiles stuff to Java bytecode and whatever happens afterwards. Okay, so the demo is going to produce some audio signals for you from scratch. So the first thing we need is something like a waveform generator. And the general idea of data stream programming is most of the computations are repeated all over in a big loop every time the clock ticks. And if you want to have interesting behavior, add some delay in the behavior, especially delay feedback. And a very nice example of this is this little box. The delta is a single-step delay, so we have a feedback of two steps, and when we take a clever linear combination of the two, you end up with a numerically fairly good sine wave generator. The parameter that goes in here is the stepping phase angle, and that we have so program this thing. So the general idea is we have a box, has an output, and there's some computations. There is this multiplication constant, and then we have a delayed version of the output signal, and we have a delayed version of that one, and the output is a linear combination. So unfortunately, the diagram looks simple, but there's a lot of cheating going on here. The first thing we cheat about is, look at this, the initial values of the delayed lines are missing, and you can't just put in zeros because you're not going to get a sine wave from that. And it turns out that you have to encode the initial phase and also the amplitude in a fairly complicated way to the initial values. So initialization is just as complicated as the actual computation that thing does every clock cycle. And initialization in real-time systems is always a very fuzzy sort of thing. So we have to do two things. We have to fill in the initial values. These are going to work. Make this a little faster. So this. And the second thing, there's this parameter epsilon, which has a different role because it's not a data stream, it's a constant. And constants in real time are much more complicated than you would think at first. And we solve this problem by stage metaprogramming. We just open a new stage here as a hash mark. And from inside the stage, everything outside looks constant. It's frozen at time. So the actual implementation is a function that takes this parameter, and then as its output is just a curly brace, is just a lambda expression. And the output is the component with a correctly parameterized and instantiated that we're looking for. Now, first of all, we don't have any wave generator. We don't have any generator, and of course, we just get a lot of static noise.
So you have to listen if you hear the sound. If you recognize what I'm playing.
No, I don't think so.
You sure, yeah?
Jingle bells.
Almost. So let's see what happens. Nothing. So what's wrong? Yeah, I'm going to cheat probably. No? Can you try? No. I'm not quite sure what happened, but I can cheat.
Who likes notion?
I will have to figure out the mistake I made. Okay, so now the basic sounds okay, but there's a lot of problems there. In particular, the attack doesn't sound very nice because the default implementation is just turns on the volume on the way when the key is pressed, and it gives these sort of ugly sounds. So we need something more sophisticated for the envelope, and there's a standard model which can be described like this. It's an ADSR envelope generator specified as a hybrid automaton. Unfortunately, this doesn't go very well with this kind of diagram because the meaning of the nodes and errors is a very different one. This one is about data flow, and that one is about control flow. Because here the errors are transitions between nodes. And what can we do about that? Well, we can discretize this thing. We end up with an ordinary automaton, and then we use the standard means for programming automaton, functional programming that's recursion. Well, we don't have recursion, but we have delayed feedback. That's just as good. On a state type, which is an algebraic data type. It codes all the different modes. I'm not going to program this actually because this is not about live coding, but I'm going to highlight the details for you. You can stare at the code in the paper. It's not that complicated. So we have some parameters as before. These are these little A, D, S, and R things, which are functions here. So you can put in any first order differential equation you like for the envelope form. And then we get a box that has a gate input and some output, of course. And out comes, because we're dealing with state transitions, out comes in 2 copies, and one is the delayed version of the other one. Then we have state, also in 2 copies, which has this enumerated time for modes of this automaton. And of course, the initial state is the release state where you don't hear anything. And then we have the state transition function, which is just ordinary pattern matching on the state, gives you the new state. And yeah, the output function, which essentially plugs in the right differential equation, which is A in the attack state and so on. And then because we have discretized the whole thing, we have to care about overshooting signals. So we have some bounds here. That to make sure signals are clipped at the right level.
It's not the only case I can play in 30 seconds.
And the controls you see here actually implement this component interface and are plugged in for AD as a part of this place here. And still doesn't sound very good. That's because the sine wave with carrier signal is very, very fragile, susceptible to the distortions of all kinds of cheap hardware. So we do what people usually do. We add some
reverb.
Overdrive.
How bad?
It's going to be distorted anyways, and we can distort it right away. So let's say we multiply with some scale constant, and then we do clipping. We get lots of very nice overtones. Too much? What you see here is actually this little organ has 4 octaves, so it's 49 voices. It's fully polyphonic, so there's 49 instances of the code you saw running at CD quality, so it's fast enough for this application, obviously. Okay, that concludes our demo. So this is the current state of the implementation. You already have seen that we're mapping initialization configuration to metaprogramming. We believe there's a lot more to that idea, especially because we don't have loops. Programmable loops, we don't have recursion, we have to use this in a clever way. Then these systems usually run at different rates. Here you have audio rate for the waveform, and you have some scaled down control rate. In this case, it's scaled down by a factor of 64 for the envelope generator. So these systems who want to describe them in a single program and then slice them according to the rates everything runs in. Would like to throw in some domain-specific type systems such as units. If you have things that are measured, for instance, in dB, we would like to have physical units in the type system, so you can mix up encoding and so on. And of course, do some analysis, for example, for real-time systems, you're interested in worst-case execution times. And we believe that the semantics, because it's so rigorous, commands itself to static analysis. And finally, we are looking at some serious backends. Obviously, Java is just a toy application for real-time systems. But we can, in principle, generate code for GPUs, for signal processors. And our next project is doing some FPGA code generation for really hard control program problems in microsecond scale, but using the same front-end problem. Okay, that's
Nanoseconds.
no microseconds. Yeah.
Right. 0.1 microsecond.
So we're into the discussion already. That's,
We're done for questions.
So you mentioned that the back end was in Java, is that right?
yeah.
So do you think it would be possible to convert it into FRP in, say, the libraries that we have in? Do you have some sense of whether that's possible or not?
Yes.
Or are you doing something that's sort of has some common part that maybe is different?
No, it's absolutely possible. I can show you, it's complicated in the semantics paper, but it boils down to something like, continuation-based implementations of FRP. It's very much the same thing. We could translate it, but we get spaced out time leaks that way.
The other way around. Sorry. And the reverse translation, sort of using this as a backend for FRP, would that be a possibility?
If our preconditions on the timing model are met, yes. But we assume that everything runs at a fixed unknown rate, discrete, there are no spontaneous events. If you stick to that in FRP, you can also translate it the other way around.
Probably don't have higher order signal functions in the sense of replacing an entire circuit, if you will, with another one, or do you?
Yes, using this stage beta programming thing. The idea is every time you open a stage, you just increase the frequency of the system, so you can do reconfiguration at a lower rate and do that hierarchically. But yes, higher order functions need some careful thought.
To just clarify, you can actually reconfigure the system on the fly while it's running. Is that what you said?
Yes, we don't have an example yet because obviously the code that you write depends a lot on the runtime system. So a lot of the real-time scheduling and so on has to be done manually right now, and we don't have a running example that's dynamically reconfigured. But we had one before. We had a working compiler. Are you familiar with the Shepard phenomenon in acoustics? We had an implementation of that where sort of we simulated the code generator and it used dynamic reconfiguration a lot. We will be able to reproduce that soon.